Our next speaker, and again, moving west to Alberta, we're very glad to have our next speaker here. Miles Dyck is a professor in soil science and renewable resources at the University of Alberta. He grew up on a farm just outside of Swift Current, and it says you became fascinated with the origin of soil and the landscapes there, so that prompted you off to University of Saskatchewan for your bachelor's and master's degrees. You've been at the University of Manitoba since 2008, Alberta. But you've been working on the famous Breton plots. Breton, the Alberta provincial soil, unofficially. And anyways, we'd welcome you here today to talk about some of these really neat long-term interactions that you're seeing over the long term with nutrients in your observations. So welcome, Miles.
Thank you, John, and it's my pleasure to be here this morning. So I'll start off. Interestingly enough, I found this in the Western Producer a while back now, but it's about North Dakota. And so talking about how the fertilizer, they had to change the fertilizer recommendations for fields that had been under no-till for a while. Compared to conventional management. So this is an example of how a change in management can affect soil properties and processes. And so that's kind of a theme that's going to run throughout my presentation here. And so I guess in Western Canada and the Northern Great Plains, we've seen a lot of changes over the last 20, 30 years, a lot more diversity in crops and crop rotations, and a lot more higher yielding cultivars. So this is bound to affect our nutrient cycling. And oddly enough, we can show examples of this, the differences between rotation and nutrient dynamics in an experiment that's 90 years old. And that's the Breton classical plots, established near the town of Breton, Alberta. Breton, Alberta is about 100 kilometers southwest of Edmonton in Alberta, in the gray soil zone. So we have a picture here with, let's see if I can get, that's okay. We have two rotations in this experiment. You can see here a 5-year and that WOBHH, that's a wheat, oats, barley, hay rotation. I'm going to call it a cereal forage rotation just to make life a little easier. And then there's a 2-year wheat fallow rotation. And superimposed on top of these rotations, we have 11 kind of fertilizer treatments, but they really reduced down to 8 different fertility treatments because some of the controls are replicated and one of the NPKS treatments is replicated. And so you can see on the treatments here, we have the full NPKS as fertilizer, we have a manure treatment, and then we have a number of nutrient exclusion treatments where one of NPK or S is excluded from the treatment, so we can look at the individual responses to the individual nutrients. The N source is urea, phosphorus source is super triple phosphate, K source is potash, and the sulfur source has been elemental sulfur since 1980. And the rates depend on the rotation phase. We don't apply any N in the alfalfa brome hay phase, but in the wheat, we depends on the rotation. The wheat fallow gets 90 kilograms of N. The cereal forage wheat gets 50 kilograms of N, the oats get 75, and the barley also get 50, and then the P, K, and S are fairly consistent. And off the top of my head now, I know the S is 20 and the P and K are fairly typical rates for the area. So here that's a little more apparent to you. This site is unique. We're in the gray soil zone. So this is the native vegetation here is boreal forest. And so the soils under that forest are pretty different than our typical black chernozems that we're used to around Edmonton and around Winnipeg here as well. And so really these soils presented a pretty significant challenge when they were first converted over to agriculture. In the boreal forest, most of the organic matter is on top of the mineral soil in the forest floor. And when that landscape gets converted over to agriculture, a lot of that carbon, organic matter is lost. And so you're starting off with a very kind of organic matter poor topsoil, which was a much different story in the grassland ecoregions. And so these soils mounted some significant challenges to the early farmers, but as we can see, they respond fairly quickly to changes in management, which has been interesting. So this graph here is the right on. Okay, showing total carbon and total nitrogen, and the different color bars represent the two different rotations. And on the x-axis here, we have the different nutrient or fertilizer treatments. So right away, you see a rotation effect, which is, fairly what would be expected. We have cropping every year in the 5-year rotation, and we have 2 years of perennials, actually close to 3 because the alfalfa brome is underseeded with the barley. Barley is a nurse crop for the forages. So we have a lot more carbon and nitrogen inputs in the 5-year rotation. And then you can see the effects of the nutrient management superimposed on top of that. I'm going to focus on wheat because wheat is the common crop between the two rotations. And I just chose the most recent 12 years and calculated a 12-year average. As you might have noticed from the experimental design, we don't have very good spatial replication because Dr. Fisher was, just publishing his work on statistics during the time these plots were established. So we don't have great spatial replication, but we do have replication in time. And so here's the two different rotations. Here's the 5-year rotation and the wheat fallow rotation. I got bushels per acre in the middle there, which correspond to these yields in kilograms per hectare. And so you see, and again, the different fertility treatments on the x-axis here. And you can see a rotation effect with respect to the response to the fertilizers. And so that's what I'm really going to focus on for the rest of the presentation, is that rotation effect on the nutrient response. So rather than dwell too long here, I'll keep going. So these graphs look very similar, but this is nitrogen uptake in the grain and the straw in the wheat phase of these rotations. So crop N recovery, I'm going to call that. In pounds of N per acre and kilograms of N per hectare. And so you see it shows the similar pattern to the yield response in the different rotations and the different fertility treatments. So now I'm gonna, these bar graphs are quite busy. I'm gonna try and break it down a little simpler and look at one nutrient at a time. And so I'm gonna try and just kind of symbolically represent response to the different nutrients. So here's an example with wheat yield. Over here in the 5-year rotation, I blocked out these other treatments, and I'm just comparing the NPKS treatment to the PKS treatment. So this isolates the response to N of wheat over the last 12 years. So we see in the 5-year rotation a really small response to applied nitrogen, compared to the wheat fallow rotation, which has a very high response to applied nitrogen. And so part of that is rate. In the 5-year rotation, wheat only gets 50 kilograms of N as urea. In the wheat fallow rotation, it gets 90. But in the 5-year rotation, we have a lot of N supplied through biological fixation in those forages, in the forage phases. So this response to N fertilizer is a little bit muted because of all the extra soil N that's available. And again, this is just the N uptake, so same kind of pattern with respect to yield. Okay, so when I break this down in these more simplified graphs, I did this for nitrogen. So here's the yield response to nitrogen for the 5-year rotation. Here's the yield response to nitrogen for the wheat fallow rotation. This side, we have the N uptake response to nitrogen for the 5-year and the N uptake response on the wheat fallow. Okay, and so now we also have the yield response to phosphorus in the 2 different rotations, or the N uptake response to phosphorus in the 2 different rotations, potassium and sulfur. Okay, so this is the response of the yield or the nitrogen uptake to applied nitrogen, phosphorus, potassium, and sulfur. And again, you see a very significant rotation effect. In the 5-year rotation, we have a much stronger response to phosphorus, sulfur, and potassium than we do in the wheat fallow rotation. And that is just a function of the different crops in the 5-year rotation. Those forages remove a lot of phosphorus, potassium, and sulfur. And so over time, we see a much greater response of wheat to potassium, phosphorus, and sulfur fertilization. And correspondingly, the N uptake as well shows the same response to the different fertilizers. Okay, so for the rest, for phosphorus, potassium, and sulfur, missed the label down here. So these graphs you can look at. So this is the phosphorus uptake, crop phosphorus recovery above ground in response to nitrogen, phosphorus, potassium, and sulfur fertilizer application. Okay, for the 2 different rotations, same with crop K recovery or K uptake for the 2 different rotations as a function of nitrogen, phosphorus, potassium, sulfur fertilizer, and the sulfur below. And so again, you see those very significant rotation effects. So I'm gonna, the next few slides, I'm gonna try and just break it down. There's a lot of information here. So we already talked a little bit about yield and crop nitrogen recovery. If we compare the 2 rotations, a lot of the differences can be explained in those biological N additions from the forage phase. And a lot of much greater export of nutrients because of those forages and because we have a crop every year, whereas with the wheat fallow rotation, there's only a crop every 2nd year. So basically, the long-term nutrient balances that result because of the rotation that's been established really impact over the long term, impact the response of the wheat to the different fertilizers. Phosphorus recovery. So here I have the bar graphs below and my little schematic diagrams on the left. So if we compare the crop phosphorus recovery in the 2 rotations, again, those forages, those perennial forages, the alfalfa biological fixation plays a role. We have this interaction with potassium in the 5-year rotation, okay, because we've developed a potassium deficiency over the long term. We see that application of potassium seems to have a small effect on the uptake or the recovery of phosphorus. And sulfur as well. That response to sulfur also has an impact on the crop recovery of phosphorus. And in the 5-year rotation, we see in both rotations the biggest impact on crop P recovery is phosphorus fertilization, which makes sense. In the 5-year rotation, there's a much bigger impact of nitrogen on crop phosphorus recovery. And again, a little small impact of sulfur, because these boreal soils are typically deficient in sulfur as well. So even though we don't see a strong response to sulfur in the wheat fallow rotation, it still has some impact on the recovery of the other nutrients. Potassium is interesting. This is one of the few areas in Alberta where we see now a response to potassium application in wheat. And again, we see this difference in the rotations. So this is, again, because of the biological fixation in the 5-year, this bar only represents the response of potassium recovery to applied nitrogen, but that's not the whole story because there's a lot of nitrogen in the soil from those previous phases. So that link between nitrogen and potassium is still there, probably just as strong in the 5-year as the wheat fallow. Same story for phosphorus, probably just not apparent because we're looking only at fertilizer N effects. And again, we see right across the board the impact of phosphorus and sulfur on K uptake, and of course the K fertilizer impact as well. The yield, there isn't a strong response of wheat to potassium in the wheat fallow rotation. In fact, no response at all. But we still do see a response in crop recovery of potassium with potassium application in the wheat fallow. Sulfur recovery. And again, in the 5-year rotation, because we have that much stronger response to sulfur in the 5-year rotation in wheat, we see a much bigger impact and as well the effect of the other fertilizer nutrients also. And no effect of potassium on sulfur uptake in the wheat fallow rotation. So that's running really quick here, but we're close to coffee break, so I'll just keep trucking. So I'm just going to summarize some of those observations in these next few slides, and I'm going to introduce this, I'll call it a functional notation. Since I have a soil physics background, I'll use a mathematical rotation. So N as a function of P, that's crop N recovery as a function of phosphorus fertilizer application. N would be considered the dependent variable, P is independent, and in reality, though, they're actually both non-independent, as everything is in agriculture. But and again, phosphorus, P is a function of N, that's crop phosphorus recovery as a function of N fertilizer. So those are just kind of how you want to interpret these next slides. So the summary of interactions involving nitrogen. Nitrogen recovery is a function of phosphorus fertilization, and phosphorus recovery is a function of nitrogen fertilization in both rotations. And the magnitude of that interaction is proportional to the crop responses. So these, these are all very straightforward, and I'm really glad and fortunate that the data support what seem to be obvious conclusions in my mind. Crop N recovery is a function of potassium fertilization only in the 5-year rotation. Because there's a potassium deficiency that's developed over time in that rotation because of the forages. And so the inverse is also true. Crop nitrogen recovery is a function of sulfur, and sulfur crop recovery is a function of nitrogen in both rotations, and the magnitude of that interaction is proportional to the response of the crop to those two nutrients. So phosphorus and potassium and sulfur, the other 3 remaining ones. So K and P interact in both rotations, but it's mostly the effect of potassium fertilization and crop phosphorus recovery is really only apparent in the 5-year rotation. The effect, crop responds in P to both rotations, but only to K in the 5-year. So sulfur recovery, crop sulfur recovery is a function of phosphorus and vice versa in both rotations in proportion to their magnitude of their response. And crop K recovery is a function of S in both rotations, but crop S recovery is a function of K is only apparent in the 5-year rotation because the crop responds to S in both rotations, but only responds to K in the 5-year rotation. So if you think I am thinking in circles here, here's another slide where I'm thinking in circles. So crop recovery and response to the fertilizers depends on the soil nutrient stocks and the availability of the nutrients in those stocks. And all those we see have been influenced by the long-term management, the rotation, the crop and the varieties, if we extend it out, the growing conditions, fertilization history. So the magnitude of the interactions between nutrients depends on the magnitude of the crop response to those fertilizer nutrients, which depends on the availability of those nutrients in the soil nutrient stocks, which goes back to these management factors: rotation, fertilization history. We'll look at some of the practical implications of that in a few slides. Here's another effect here. I didn't really show it on the initial slide, but we do have pH issues in these gray soils as well. And so on the 5-year rotation, we have a liming treatment. One half of the plot receives lime regularly. pH is tested every 5 years, and we apply lime if necessary. And then the east half of the plot has remained without lime since the experiment was established. Okay, so if you look at the wheat N recovery for the and the P, K, and S recovery and the effects of lime on those nutrients, there is a significant effect of soil pH as well. So that's another factor that's affecting our crop nutrient recoveries. So you can see the effects, and you know this. That's really good information that Ryan had about the 0 to 3 inch sample, because we sample 0 to 6 or 0 to 15 centimeters, and we don't see a really large difference in pH between the lime and the no lime treatments, but there is a significant agronomic effect with that small change in pH, and we're hovering right around the 6 and the 5.5 mark, which is where the results, which is where that threshold seems to lie. So John encouraged me to make this practical, and so I was thinking, if I was a farmer and I saw these results, what would I do? And so this is, I think, some reasonably practical applications of this research. So these days, you know, I think it's not out of the question if farmers are willing to develop field-specific nutrient budgets, to develop that over time, record keeping, basically. So yield monitors and weighing wagons are now common. Right? John's just been working on updating the crop nutrient removals for Western Canada in the last 30 years. So we have yields. We can look up in the literature how much nutrient is removed as a result of those yields, or we can even take grain and straw samples and get measurements as well. So nutrient removals from a field average nutrient removal, or even a zone average if there's zone management, can be documented fairly easily, I think. Those can be complemented with soil nutrient stock measurements and pH measurements about every 5 years or so. Because we're dealing with totals here, I'm recommending total concentrations for this purpose. You should measure available nutrients on a yearly basis, but if you're looking at field nutrient budgets, you can get away with less frequent samples and total levels for the nutrient stocks. And of course, it's much easier to document fertilizer applications now, and that's required. And so over time, for each field or each zone in a field, you can develop this trend of nutrient removals, nutrient additions over time, and you can see where you're at on the balance sheet. And as you can see from the Breton plots, that these rotations and fertilization treatments, they do, over time, they do result in changes in soil nutrient stocks, in total nutrient levels in the top 6 inches. And those changes are highlighted in green here. So if you compare NPKs to the nutrient exclusion treatment, right, we see that effect of no nitrogen addition over time. We see the effect of the phosphorus exclusion and the sulfur exclusion in those treatments. So this is something I think would be useful and practical to be applied on farm. Right, and then if you want to step it up and do some deluxe record keeping, right? There's fertilizer occlusion strips, and I was really happy to hear about some people using those yesterday. Some of the agronomists in here and your clients are using exclusion strips, and that's great. So that shows you if your crop is responding to applied nutrients, which is very useful information. And so you can compare the crop nutrient recovery in the exclusion strip compared to the rest of the field, just to show how much difference that fertilizer is making, to see if your target yield is reasonable. And it is, that's an assay of available soil nutrient stocks. So that's even more information, I think, than a soil test for available nutrients. It gives you an actual uptake given the field conditions in that growing season. And so allows you something to kind of benchmark against your soil tests as well. And I think it helps manage risk, right? So if you have those nutrient balances documented, you have that historical database to help support your decisions from year to year for your fertilizer management plan. And so you can, maybe if we always want to achieve high yield, but there's always a risk associated with that because you don't know if you're going to have the weather for it. So if you can manage your nutrient stocks so you're in a position, if you fertilize for average yield, and then in the wet years, you're in a position to have your soil nutrient mineralization, your nitrogen mineralization kick in, you're in a lower risk situation than if you're trying to push yield every year. Right, so I've got 3 scenarios here. If you have a balanced nutrient budget and through your exclusion strips, you see that your crop is still responding to applied nutrients, right? You just replace the nutrient removals in the harvest. If you have a negative budget, if you're removing more nutrients than are applied, and you have a measurable crop response to the applied nutrients, well then it's time to try and build up those soil reserves a little more. If you have a positive budget, if you're adding more nutrients than you're removing, and you don't see a large response to applied nutrients, then you can draw down those soil nutrients for a little while and reduce your fertilizer applications. And there's always room to be innovative. So this is results from Breton as well, and we participated in the Soil Health Institute's North American project to assess soil health measurements. And we found this one soil health indicator, the autoclave citric acid extractable protein in soil. It is a good indicator of potentially available nitrogen. And so this is a relative yield for all of our long-term rotations, and we saw a pretty strong correlation between the ACE protein measured in only 1 year, and there's a high correlation to the 12-year yield average. So there's some of these new soil tests that are coming down that show some promise to be a little more useful. So with that, I will be happy to answer any questions if there's time.
Very good. Thank you, Miles. Okay, thank you, Marla. Were there any questions from the crowd here? Okay. How about?
Well, it's Curtis Cavers, John heard, and of course he can't be here in person for some awful reason. But he does want to just wonder about speculating on differences you would observe if the management in that study had been changed or tweaked rather than held constant for tracking the trends. Would we have seen differences be larger, or would they be masked if we had adjusted to current agronomic practices like different varieties, crop nutrition levels, pest control, etc.?
Oh, right, that's a great question, and that's maybe I should have added that we have adjusted the varieties. We do keep relatively current with the best varieties for the region that are recommended, and we did adjust the nutrient rates in 1980 to keep up with those greater demands from the newer varieties. But that's still a good question. I think, you know, the response that you will see depends on what kind of change that is implemented. So, I mean, I think, you know, the first slide I showed, the change was the tillage regime. That showed a very large change to the nitrogen dynamics. And I think now with just the increase in the crop diversity in the rotations, I think that's a fairly large change. That's going to influence nitrogen dynamics a lot. So it depends on the type of change. I think any change in rotation diversity or, for example, perennials in the rotation, you're going to see a large change and different kinds of changes, different, you know, changing from conventional fertilizers to slow release fertilizers. I think you'll see a much more muted response, for example.
Just two questions. One, for the plots, were they established on like virgin ground, like once the trees were cleared? And then if, just to give some context for everyone, the environment that the crops are being grown in, heat units, moisture received.
Sure, that's a good question. So the widespread agriculture was implemented in the Breton area in 1919. So the farmer that owned this land originally had been farming for about 10 years before these experiments were established. And in that 10 years, I don't think there would have been a lot of change. Fertilizers were not widely used at that time. And yeah, so there was some agriculture before the experiment. So it wasn't completely newly converted land, but it was very close. And the growing conditions were in the subhumid area. Annual average precipitation is around 450 millimeters. And it's fairly cool. So growing degree days are about 1,200 for the growing season. Yeah, so it's a much cooler, as Ben mentioned yesterday with his soil mineralization study, that it's the coolest site. One of the coolest areas in Western Canada for agriculture.
Okay, thank you very much, Miles. You're with us for the rest of the day, so if you have more questions, it's your wonderful parting gift. Thank you.